Welcome to EPG Pathshala. The subject we are looking at is computer science and computer networks in that. So, in the past few modules we have been looking at application layer and transport layer. So, now starting from this module we will be looking at network layer. So, we will start today with what are the functions of the network layer and some of the issues that we have with basic network layer functions. So, the two important functions of network layer are routing and forwarding, and we will also look at something that we call as switching. So, we will look at circuit switching, or in fact virtual circuit switching versus packet switching, and we will look at the datagram approach which is used in the current TCP/IP networks, which is in the IP protocol. Okay. So, if you look at the network layer, the basic function of the network layer is to transport segments from the sending host to the receiving host. So, on the sending side what we expect it to do is encapsulate the segment into datagrams and send it into the network, and on the receiving side you have to deliver the segment to the transport layer. So, this is the network layers interface to the transport layer, and network layer protocols must reside at every host and every router because it has to go through the entire network, and the router as part of the network layer function will have to examine the header field in all the packets that are coming, okay, and it will have to forward it. Okay. This is what we know as the basic function of the network layer. Okay. So, every end system will have all the 5 layers as we can see, and all the other routers in between will have 3 layers up to the network layer. Okay. So, network layer is definitely there in all the systems including the routers, and when a packet has to be sent, you can see that it will go through this up to the network layer, through the network layer through the various devices, come to the network layer at the end host, and finally reach the application. So, this is basically the flow that is going to happen, that happens. All we need to understand is what happens at the network layer for this flow to happen effectively. So, that is the goal of understanding the network layer's function. So, the two key functions that we said are forwarding and routing. Okay. So, how do we differentiate between these two terms? Forwarding is moving the packets from the router's input to the appropriate output. Remember that the router will have multiple interfaces. So, packet coming in on one interface will have to be sent to another interface. So, moving it from one interface to one of the appropriate output. So, that is the forwarding function. Routing function is determining the route that is to be taken by the packets from the source to the destination. So, you can see that there may be multiple paths available from source to destination. So, identifying the path that is to be taken from the source to the destination is part of the routing function. So, we have routing algorithms which are used for identifying these paths, and based on these paths you have information that is available at the routers, and based on that information the forwarding will take place. So, there is a relationship between forwarding and routing. In order for forwarding to take place, routing should have happened. Okay. So, this is the interplay that we have between routing and forwarding. So, you will see that there is a routing algorithm, right, which will determine the end-to-end path through the network, and based on that it will construct what are called as local forwarding tables at each router. So, this forwarding table will have information as to what is expected of this particular router, right. So, when a packet comes in with a particular header value, on which output link it should be sent. Okay. So, that is the information that you expect to see in this. Okay. And based on this the packet will be sent. There are forwarding tables like this available at each of the routers. So, at each of the routers a packet coming in will be examined, and based on that will get forwarded, and it will be able to finally reach the destination. Okay. This is basically what happens between routing and forwarding. Okay. So, another concept that we often come across when we talk about networks is something called switching. Okay. So, switching and forwarding. So, the question again is, how does the switch or the router decide which output port to place each packet on? As we just said, it will be based on the information that is there in the header of the packet. There will be some identification in the packet's header which tells us that okay, this packet has to be sent in this particular direction, okay, or to this particular port, this output port. Okay. So, that is what we normally do. Now, in order to do this, okay, there are two different approaches that are taken. Okay. So, one is called the connectionless approach or the datagram approach. The other is a connection oriented approach or a virtual circuit approach. Okay. There is also a third approach which is source routing, which is less common though. Okay. So, these are the two things which we will be looking at, the datagram or connectionless approach. Now, incidentally that is the one that is used in the IP network. So, obviously we will be focusing on this quite a bit. But before that, we will also take a look at the other option which is available, which is the virtual circuit approach or the connection oriented approach. Okay. So, when we talk of these two approaches is when this term switching basically comes in. So, we say this datagram or connectionless approach is a packet switched approach, and the other one is a circuit switched approach or a virtual circuit switched approach. Okay. Now, there are different ways in which these terms switching, routing get used, but what we will be restricting ourselves to is that that it specifies the manner in which this function basically takes place, the approach basically takes place, okay, or the approach that is actually used. Okay. So, let us look at both these approaches, the connection oriented approach and the connectionless approach. So, as I said, datagram approach, a datagram network uses the connectionless service, and a virtual circuit network uses a connection oriented service. So, this is very analogous to our TCP and UDP, because we know TCP provides a connection oriented approach and UDP provides a connectionless transport layer service. But the difference is that the service here is a host to host service, okay, and there is no choice. In the case of TCP UDP, the application has a choice of choosing whether it wants to use TCP or UDP, right. Whereas here with respect to a network, we really do not have a choice. The network provides you one or the other, either it is a packet switch network or it is a circuit switch network or a virtual circuit switch network. Okay. And the implementation actually takes place in the network core and not at the end systems as such. Of course, the end systems also participate, but most of the work gets done at the network core. Okay. So, so if you are using a virtual circuit switched approach, right, if you look at this virtual circuit switching mechanism, there is a third important function which comes in, which is the connection setup function. So, if you say connectionless, then we really do not have to do anything, we just take the packets, keep sending them into the network. But if it is a connection oriented approach, then obviously we know that we will have to first establish a connection and then send the packets through that connection. So, we have another important function which is coming in, which is the connection setup function. Okay. So, we need to understand how this works in the case of virtual circuit switch networks. Examples of virtual circuit switch networks are ATM, frame relay, X.25. These are all network architectures which make use of the virtual circuit switched approach. So, before the datagrams flow, the two end, or before the packets flow I should say, the two end systems, okay, the hosts and the intervening routers and switches will establish this virtual connection. That is, the routers and switches are also involved in this entire process. And if you compare the again the network and the transport layer connection service, as I said, the network layer connection service is between two hosts and it also involves the intervening routers, whereas the transport layer is basically between two processes and it is normally only at the two end systems. Okay. So, this distinction between the two, what happens in these two layers is something useful to note. So, let us just take an example of what actually happens in a virtual circuit scenario. Okay. So, just an example. So, I have one machine here, there is a number of routers through which another end system is connected. So, in the initial connection setup phase, the first step that will take place is that a call will be initiated, okay, and it will notify to the other end that there is an incoming call. You can see that this is very, very similar to what happens in the case of a telephone connection that we are all very used to, right. So, you get a call that comes in, then you pick up the phone and then the connection is established. So, that is a complete circuit switched approach. Okay. So, we are talking about something which is similar to that, but it is a virtual circuit that we are looking at over here. Okay. So, this is the first setup, that a call is initiated. The second step will be that you will accept the call, and once the call is accepted and that information is passed on to the other end, the call is connected. And remember that when this is done, there is some processing that happens at each of the routers through which this call has to take place. Okay. And then once the call is connected, now you can start sending the data. So, data starts flowing from one end to the other end through this connection that has been established. Okay. So, this is basically what we expect to take place in a virtual circuit switched network. So, a virtual circuit that we are talking about, so this whatever we talk, just as we have a physical circuit in the case of a circuit switch network, which is a complete physical connection from one end to the other. When we are talking about a data network and we talk about a virtual circuit in that context, okay, a virtual circuit we can say consists of three entities. One is a path from the source to the destination, and something called virtual circuit numbers, which identifies this virtual circuit on each link along the path. Okay. So, you have a number, right, for each link along the path, okay, which is called as a VC number. So, since it is a virtual circuit, which automatically it also means that multiple virtual circuits can actually exist on one single physical circuit. Okay? So, you need to distinguish between these, which is why we need this VC numbers. And it also consists of entries in the forwarding tables in the routers which are along the path. So, now these entries in the forwarding tables will make use of these VC numbers in order to do the forwarding. Okay? So, this is what we mean by a virtual circuit connection that is to be set up. Okay. So, a packet which is coming in from a source which belongs to a particular VC will carry the VC number, okay, rather than the full destination address. Okay. So, this is one of the major distinctions between a virtual circuit network and a datagram network. So, in a virtual circuit network, once the circuit is set up, packets are sent along that virtual circuit need not carry the full destination address, because you have identified the path that is to be taken, you have set up everything, and you also given some number for this path. So, packets that are coming in now need not carry the full destination address, instead they need to carry this path identification, which is why they will carry the VC number. Okay. And normally the VC number is smaller than the destination address, so which means that the overhead that you have per packet will also be less. Okay. And this VC number can actually even be changed at each link. It is not necessary that you will have one single VC number for the entire path. Okay. These numbers can change at each of the switches in between. Okay. So, the new VC number that is to be used at every switch will come from that table itself. So, we will see an example as to how this is actually done. So, by having a series of VC numbers which identify a path, okay, your complete path is basically set up, okay, and the packets get forwarded along that particular path. Okay. Source to destination path that we have behaves pretty much like a telephone circuit, as we said. So, which uses circuit switching, okay, both performance wise and with respect to the network actions along the source to the destination path. Okay. What we mean by this is, in a circuit switch network we get very good performance. The delays are low because at each switch in between there is not much of processing to be done, because all the processing required for forwarding the messages has already been done. It has been set up, it has already been done at the time of connection setup. Okay. So, there is very high performance in the sense that the rate at which things can go through the network is very high. Okay. But what is required is that each switch on the source to destination path has to maintain some state for each passing connection. Okay. So, it is a stateful approach. So, every router or switch has to maintain some state information. It maintains the state information as basically an entry in the VC tables. Just as you have forwarding tables, we have VC tables or virtual circuit tables. Okay. So, in each switch you have VC tables where the information about each virtual circuit is maintained. Okay. Another advantage of this is that when a virtual circuit is established, you can also allocate resources for this particular virtual connection in that switch. So, for instance, bandwidth, buffer, okay, all these things can be allocated. Now, obviously, we know that allocation of resources will help in improving performance, because your dedicated resources obviously will give you predictable performance. You can have predictable service. So, if I have a quality of service that I need to meet, it is easy to meet that quality of service with a virtual circuit approach, because I can dedicate resources for a particular virtual circuit even before that circuit, before data starts flowing on that circuit. So, at the time of connection establishment, I can say whether this much of service can be given or not. So, you admit a connection only if you are sure that you can meet the services. So, you are able to give guarantees in terms of the service. Okay. So, those are the advantages of this virtual circuit approach, which again is very similar to what you have in the case of circuit switched approach. Okay. So, which is why we call it as a virtual circuit switched approach as such. Okay. So, if you look at the, we said that the VC state is maintained in the VC forwarding tables. Okay. So, let us look at what actually will be there in the VC forward. At every router, this kind of a table will exist. So, what will be there in this table? It will say what is the incoming interface. Okay. For every router, there are obviously multiple interfaces. So, what is the incoming interface? What is the incoming VC number? What is the number with which packets on this VC will come in this? Okay. And corresponding to this incoming interface, if a packet comes with a particular VC number, what is the outgoing interface on which it has to be sent, and what will be the outgoing VC number? So, in this example, suppose let us say this was a VC that is being set. A virtual path is set from here to here, the circuit, which says that packets will come in from here with a number of 12, they will go from here to here with a number of 22, and from here they will be sent out with a number of 32. So, this is the virtual path that I am looking at. Okay. So, now the corresponding table here will be, the first entry corresponds to that. It is coming in on interface 1 for this router. It will come with a virtual circuit number of 12, it will have to be sent out on the outgoing interface 3, which corresponds to this link, and it will go with the outgoing VC number of 22. Okay. So, this is the information you will have at this router. Similar table will be maintained at the other routers as well, and using this table you will do the actual forwarding of the packets. So, if you look at these VC table entries, these are the properties that we need to keep track of. So, there is one entry in the VC table, every single entry in the VC table on a switch will contain the following information. So, as we said, it has a virtual circuit identifier which uniquely identifies the connection at the switch, okay, and it will be carried in the header of all the packets which belong to this connection. Okay, so, that is the first part. Second is, as we saw, it has an incoming interface on which the packets for this VC will arrive at the switch. Third is the outgoing interface in which the packets for this have to leave the switch, and a different VCI, an outgoing VCI, a different VCI which is used for the outgoing packets. Okay. Now, what is the semantics of such an entry? Basically, all this says is, if a particular packet comes in on an incoming interface with this VCI, it has to be sent out on this outgoing interface with this particular different VCI. So, this is what this VC table tells us. So, the amount of processing that needs to be done when a packet actually arrives, you can see is very, very small. Just look at this one table lookup and it tells you exactly what is to be done, which is why the processing of the packets at each of the routers can become very, very fast. Okay. So, that is basically what happens in this. So, this combination of this VCI and the interface, right, this combination, that is what uniquely identifies the virtual connection. So, which means that on a different interface you could have the same VCI used. Okay. So, just the VCI alone is not enough, it is the combination of the interface and the VCI which will uniquely identify the connection. Okay. And of course, there can be many virtual connections which are established in the switch at a single point of time, because they would correspond to different paths. Okay. So, there will be many virtual connections. Okay. And the third point to note is that the incoming and the outgoing VCI values need not be the same. They could be the same, but they need not be the same, and they are normally not the same. So, which means the virtual circuit identifier that you are talking about is not a globally significant identifier, it only has local significance. That is, on that link it has to be a unique value, okay, to differentiate it from other VCs which exist on that particular link. Okay. So, we say that its scope is local, it has a local link level scope. Okay. And whenever a new connection is created, we need to assign a new VCI, which is an unused VCI for the connection on that particular link. Okay. So, along the connection that is required for the end-to-end path. So, at every link you will have to establish a new entry which will consist of a new VCI value for that. Okay. Right. So, how do we establish this virtual circuit connection? So, once the connection is established, once all these information is there, you can look at this and forward the packet. That is a simple part. So, the entire complexity here comes into how this virtual circuit connection is established in the first place. Now, here there are two approaches. Okay. One is a kind of a manual approach where the network administrator will configure the state in each of the switches. Okay. So, this is called as a permanent VC. So, which means once it is configured, it remains forever. Okay. Of course, the network administrator can delete this. Okay. So, you can look at it as a long lived VC. So, if something like a leased connection where you already set up things, you can go in for this kind of an approach. But most of the other cases, we would like something which can be changed dynamically. Okay. Then in that case, we need to have some kind of a signaling protocol that has to be used. That is, the host will have to send some message into the network which tells the different routers which are there in the network to establish the state. Okay. So, we use some kind of a signaling for this, and then we call that virtual circuit which is established like this in a dynamic manner as a switched virtual circuit. Okay. It is not a permanent virtual circuit, it is called as a switched virtual circuit. Okay. And the host can set up and delete such virtual circuits dynamically. Okay. The network administrator need not get involved in this. By following some protocol, part of that protocol will have the signaling as part of that protocol, and using the signaling mechanism we will be able to establish the state and remove the state as well. Okay. So, we will take a look at how the state establishment gets done. So, we will start with first a manual setup, so that once we understand the manual setup, it is very easy to also understand the steps that have to be followed for a signaling mechanism as well. Okay. So, let us say we want to set up from host A to host B. Okay. So, we know that the path to be taken will be from switch 1 to switch 2 to switch 3 through this. Okay. So, the first thing that the administrator has to do is to identify the path through the network from A to B. Okay. So, this is identified. So, once he has done this, now the administrator will have to make the entries at each of the switches. So, let us look at what will have to be done for that. Okay. So, the first thing that the administrator will have to do is pick a VCI value which is currently not used on the link for that particular connection. Okay. So, from let us say from host A to switch 1, that is the first link that we have, right. So, assume that the VCI value 5 is chosen for the link from host A to switch 1, okay. This information is identified at switch 1, okay. And 11 is the value is chosen from switch 1 to switch 2, okay. From here to here we are going to use a value of 11. So, the switch 1 will have an entry in the VC table which says, if a packet comes in on this interface 2 with the VC value of 5, the outgoing interface will have to be 1 and the outgoing VC will be 11, okay. This is the information set up in the table. Now, remember something similar has to be done at each of the other switches as well. So, at switch 2 and switch 3, right. So, let us look at what happens. So, similarly let us say now switch 2, it knows the incoming, okay. So, now the administrator knows that initially it will come in with a value of 11, let us say it will go out to the value of 7. So, incoming interface is 3, incoming VC is 11, outgoing interface is 2, outgoing VC is 7. So, this information will be set up at switch 2. At switch 3 similarly, now you have to choose a value for this interface, right. So, for this interface, let us say it is choosing outgoing VC of 4. So, which means it will set this entry saying incoming interface 0, value coming in is 7, remember this 7 and this 7 will have to match, and outgoing interface is 1, it will go out with a VC value of 4, okay. So, once these 3 tables are set up, now packets can start flowing from A to B, okay. And how will they flow? Packets coming in from host A will come with a VC value of 5, and using this table it will be sent out with a VC value of 11, and that will come into this switch with a VC value of 11, it will be sent out to the VC value of 7, it will come to this switch, it will come in with a VC value of 7 and go out to the VC value of 4. So, as far as host B is concerned, it will think that the connection from A is going to come with the VC value of 4. So, his identification of this connection is VC value 4, whereas his identification, A's identification of the connection will be a VC value of 5 that we started with, okay. So, this is basically what will happen. So, once this process is set up using the virtual circuit switching mechanism, packets can be forwarded. Okay, so this is basically what we said. So, at data transfer at each of the switches, this is what will happen. So, comes in with value of 5, it goes out on this with a value of 11. Okay, so you can see that this VC identifier which is there in the packet header will be changed to a value of 11 when it is sent out on this out of this switch. Similarly, at the next step, you can see that here it comes in with a value of 11, will be sent out with a value of 7, outgoing VC value will be 7. So, there is a change in the VCI value in the header, okay. So, there is a change in the header itself, okay, that is to be noted. Similarly, here it is coming in with a value of 7 will be sent out to the VC value or VCI value of 4, okay. So, this is actually how the forwarding will take place, okay. Now, if we were, this is what we saw right now is a manual setup, okay. So, if the signaling has to take place, right. So, now let us look at exactly what are the various steps that need to be followed, okay. It basically starts like this. Almost everything that we did manually now will have to be done, but it has to be done through a signaling mechanism, okay. So, to start the signaling process, what host A will first do is, it will send a setup message which is like a connection request message into the network, that is to the switch 1, okay. And the information that it will have is the complete destination address of B, because switch needs to know what is the path to be taken, right. So, the complete destination address of B will be there in the connections request message. Now, when switch 1 receives this connection request, what it will do is, it knows it has to be sent to switch 2. Now, how will it know that? By looking at the destination address and by looking at its routing information that it already has, it knows that a path has to be set up through switch 2, okay. So, what it will do now is, it will set up now an entry in its VC table for this new connection that has to take place for packets coming in from A towards switch 2, okay. So, it will make an entry. Now, what is this entry? The entry will be very similar to what we saw just now, right. Same as what we saw in the previous table, incoming interface, incoming VCI, outgoing interface, outgoing VCI, okay. So, let us say switch 1 picks a value 5 for this connection, that is for the connection which is coming from A, right. Switch 1 assigns a value of 5 for this, okay. A does not know what is the value to be used, A has only given the destination address, okay. But the switch 1 will now pick up a value 5 for this connection, okay, and now will pass on the connection request to switch to the next switch, okay, switch 2. Now, what will happen at switch 2 again same process will take place. It will make an entry in that table by choosing a VC value that it will use for the connection between switch 2 and switch 1 and pass the request to switch 3. Switch 3 again will do the same thing, okay, it will process the connection request, pick a value to be used and pass that connection request finally to B. Okay. Now when the connection request reaches B, assuming that B is healthy, right, that it is willing to accept the connection from host A to host B, okay, it will allocate an incoming VCI value of 4. Okay, a request has come in, so it says, okay, for this connection I am going to use a VCI value of 4. Now obviously the value chosen must be one that is unused with respect to B. So B says, on this interface I am receiving a request, I will use an unused value of VCI value of 4, okay, and makes an entry for this and says that VCI 4 indicates that this is a packet coming from A. Now it knows the packet is coming from A because it is a setup message. In the setup message, the destination address will be there, obviously the source address will also be there. Okay, so complete source address and destination address will be there in the initial connection setup message. So B knows that packets coming from A will have to use a VCI value of 4. Okay. Now once it has done this information it will pass back to the various switches up to A. So it has to pass back the information that the connection has been set up, and you have to complete this virtual circuit setup. Okay. So what it will do is, each switch now will tell its downstream neighbor, right, the one that is downstream, okay, to use a particular VCI for this connection. Okay. So you can see what will happen here. So host B will send an acknowledgement of the connection setup to switch 3, right, which will include in the message that VCI value of 4 is the one that it has chosen. Now switch 3 will complete the VC table entry for this connection and send the acknowledgement to switch 2 specifying the VCI value is 7. Now switch 2 will again complete the VC table entry for this connection, sending an acknowledgement value of switch 1 specifying VCI value of 11. Okay. So whatever values they had chosen, right, that value they will pass on to the other person. So finally switch 1 will pass on the acknowledgement to host A, telling that you have to use the VCI value of 5 for this connection. So once this is done, all those entries that we had in those switches were all set up in all these 4 different switches, in 3 different switches. Okay. And once the switches, the connections are set up, the flow of data can take place using this VCI values. Okay. And once you have done with your data transfer, next thing you do is you tear down the connection, because you have allocated some values, entries in the table, right. So those entries have to be removed. So when host A no longer wants to send any data to host B, it will tear down the connection by sending a tear down message to switch 1. So now what switch 1 will do is it will remove the relevant entry from its table and forward the message to the other switches, and each of them will similarly delete the entries and keep forwarding their messages. Okay. And so all this complete path will be removed from the tables. So at this point, if A were to send a packet with a VCI value of 5 to switch 1, it will be dropped as if there was no connection at all, because it has removed that particular connection. Okay. So this is basically how the virtual circuit switching approach works. Basic characteristics of a virtual circuit approach are the following. Okay. So you have a connection setup delay, okay, of 1 RTT before the data is sent. But when the data is being sent, it can be sent continuously. Okay. So there is a reduced per packet overhead, because each data packet will only contain a small identifier, not the full global address, right. So just a unique link wise unique VC identifier. Okay. If a switch or a link in a connection fails, that will lead to data loss. Okay, because it means the connection is broken, and so which means you have to establish a new connection before you can start sending packets. Okay. And also the old one needs to be toned down, because it has to be removed, because you have to free up the storage space at the switches. And as I already said earlier, this can be used to support QoS, because each circuit can have a different quality of service. You can allocate different resources when the VC is set up. Okay. So you can allocate a percentage of each outgoing links bandwidth, or you can have some delay tolerance on each switch. All these are individual things that you can configure for each virtual circuit connection. So you can support QoS using this virtual circuit approach. So compared to this, when you look at the datagram approach, of course we will be looking at the datagram approach in detail when we look at the IP network. So a quick comparison of this. In a datagram approach, there is no call setup, okay, and routers do not maintain any state about the end-to-end connections. There is no network level concept of a connection. So every packet has enough information, that is the complete destination address, which decides how this packet has to be sent to towards the destination. So what happens here? You have a network, we have packets coming from here. So this fellow sends datagrams, that fellow receives datagrams. That is all that happens. Okay, and datagrams are forwarded through the network. So this is what happens in a datagram based network. So for datagram forwarding to take place, you will have destination addresses and port numbers that have to be maintained at each switches. These are the forwarding tables that will have to be maintained at each switch, right. So you can see that it is different from what we saw in the case of VCI. In VCI you will only have the VCI numbers. Here we have the complete destination address that will have to be specified. So, host A, okay, it has to be sent on port on switch 3, okay. So, something like that at each switch. This is at switch 2, host A has to be sent on port 3, host F will have to be sent on port 1 and so on, okay. This kind of information is what will be maintained here, okay. So, this is basically the difference that we have. So, in the case of datagram forwarding table, as you can see, as we already mentioned, right, you will have a routing algorithm and there will be a forwarding table that is maintained, and we are looking at datagram forwarding table for IP, for instance. You will find that instead of having just individual IP addresses, we normally have ranges of IP addresses which are specified over here, okay, and based on that the forwarding tables are set up. So, we will look at details of how IP datagram forwarding works later. So, characteristics, if you look at a datagram network as opposed to VC switching, is that it can send packet anywhere at any time, okay, because there is no connection setup required. So, you just send a packet, it gets switched through the it gets sent by the router, okay. No information about network or destination. So, when a host is sending a packet, it does not know whether the network is capable of delivering it, whether destination is available, nothing it knows. You just send packets to the network, okay. And different paths can be taken for different packets. So, each packet is routed independently of the other packets. But it is tolerant to switch or link failures, because if one particular link or switch fails, it can always be routed through another link dynamically, okay. So, that is one of the advantages that we have of the datagram approach, okay. So, this is basically to tell you the two different approaches, that the virtual circuit approach and the datagram approach. Virtual circuit approach is not very much used, primarily because the datagram approach seems to be much more robust, okay. So, we find that nowadays it is more of the datagram approach that is used. So, which is why we will be looking at the IP protocol, which uses the datagram approach fully. To summarize, what we have covered so far is that we have looked at the two basic functions, routing and forwarding, and we have looked at how virtual circuits and datagram approaches differ. Okay, we looked at the virtual circuit switching in detail, we looked at how virtual circuits are set up, how the VCIs are identified, how the virtual circuit identifiers are swapped at each of the routers, at each of the switches, okay, and how the complete data flow takes place. Okay. So, we will be continuing with the datagram approach in the subsequent lectures. Thank you.